Hello everyone, my name is Norish Zuzarig bin Ismail, and together with my friend Abdul Rahman bin Wilson, we are from Group 3. For our modern physics project, we are exploring the cosmic microwave background, or we call it CMB. So without further ado, let's get started. So why did we choose to talk about the CMB? Honestly, it's because the ultimate throwback photo. Think of it as a baby picture of the entire universe from billions of years ago. This light has been traveling through space for such a long time, nearly 14 billion years, just to reach our telescopes today. It's really the first page of the universe story, and without it, we would be pretty lost, trying to figure out how everything we see around us actually began. Now that we know the CMB is the universe's first baby photo, we need to talk about the field that started it, cosmology. Think of cosmology as the big picture vision of physics, instead of looking at just one star. We are like detectives solving the biggest mystery in existence. We're asking the massive question: how did the Big Bang happen? What are dark matter and dark energy actually doing? And where is the universe headed? It's basically the biography of the universe, and the CMB is the most important map we have to navigate its 13.8 billion year history. Alright, before we get into the light itself, we have to go back 13.8 billion years to the Big Bang. Now, forget the explosions you see in the movies, but in physics, it was more like space itself was suddenly stretching out in every direction. Imagine everything we see today packed into a tiny, super hot dot that just started growing at an unbelievable speed. As the universe expanded, it finally started to cool down, which was the key moment that allowed the first particles to form. This is the exact moment the cosmic clock started ticking, setting the stage for the light we're about to talk about next. Okay, so now that we know what cosmology is, let's look at the actual origin of the CMB for the first 380,000 years after the Big Bang. The universe was basically a giant, hot, cosmic fog. It was so packed with energy that light, particles or photons couldn't go anywhere. They just kept bumping into free electrons and getting stuck, which made the whole universe totally opaque. But then, things finally started to cool down to about 3000 Kelvin, and we hit what scientists call the Recombination era. This is when electrons finally calm down enough to pair up with protons and form the very first hydrogen atoms. The second those atoms formed, it was like the cosmic fog just cleared up instantly. Suddenly, light was finally free to zoom across space without hitting a single thing. That first light has been traveling for billions of years, and it's exactly what we're picking up with our telescopes today as the CMB. So, after all that talk about the cosmic fog clearing up, what exactly is the CMB star when we look at it today? Well, it's not like a star or a planet that you can just point it out in the sky. It's actually a faint glow of energy that is literally everywhere. I mean, no matter which way you point a telescope, up, down, left or right, you're going to find this light. Think of it like the ultimate afterglow of the Big Bang. It's kind of like a giant campfire. Even after the flames are gone, you can still feel the heat radiating from the ground and the air. The CMB is basically that leftover heat, just on a universal scale. It's the oldest physical thing we can ever detect in the cosmos, which is huge because it's the ultimate proof that our universe actually had a beginning. Plus, it gives scientists the perfect map to figure out how everything we see today was actually formed. So how did we find this light? In 1964, two guys named Penzias and Wilson were using a giant antenna to listen to space, but they kept hearing a constant annoying hiss. They even scrambled out pigeon nests because they thought the birds were causing the interference, but the hiss stayed. Eventually, they realized the noise was actually the echo of the Big Bang itself, and this accidental discovery changed physics forever and won them the Nobel Prize in 1978.
Assalamualaikum warahmatullahi wabarakatuh. My name is Abdul Rahman bin Musa, metric number S76088, and I'm gonna continue our presentations for cosmic microwave background, a relic radiation from the birth of universe. So let's continue. So for part 2, which is my part, I'm gonna start with the latest developments in CMB observation. Recent advances in technology have allowed scientists to measure the cosmic microwave background, or CMB, with extremely high precision or accuracy. The Planck satellite, operated by the European Space Agency, mapped the CMB across the entire sky, or our sky, revealing tiny temperature variations called anisotropies. These measurements allowed our scientists today to determine the key properties of this universe, including its age, which is about 13.8 billion years, and its overall composition. Planck showed that the universe is made mostly of dark energy and dark matter, with only a small fraction consisting of normal matter. The results strongly support the Big Bang theory and improve our understanding of the alien universe. Next, for CMB polarization and inflation, the ground-based experiments such as BICEP and the KEGG array located at the South Pole focus on measuring the polarization of the CMB. Polarization patterns in the CMB can provide evidence for cosmic inflation, a rapid expansion of the universe shortly after the Big Bangs. Then, these experiments search for a specific signal known as B-mode polarization, which would indicate the presence of primordial gravitational waves. Then, although no direct detection has been made, the results place strong limits on inflation models and ruled out several theoretical predictions that we have today. And last but not least, this helps our scientists today refine the theories about the universe's earliest moments, or how our universe have been made. Next, for CMB and dark matter, first, the cosmic microwave background CMB provides strong evidence for the existence of the dark matter. Tiny temperature fluctuations in the CMB show how matter was distributed in the early universe. Observations reveal that visible matter alone cannot explain the observed patterns in the CMB. The presence of dark matter is required to explain how these early density fluctuations grew into our galaxies and other galaxy clusters. Data from the Planck satellite shows that dark matter makes up about approximately 27% of the universe's total contents. Now, we go to the CMB and the expansion of our universe. The CMB also helps the scientists understand how the universe expands over time. The uniform temperature of the CMB in all directions shows that the universe now has expanded smoothly and uniformly after the Big Bang. Small variations in the CMB allow scientists to calculate the rate of expansion of the universe. These measurements support the idea that the expansion is accelerating, driven by the dark energy. And lastly, CMB observations help establish the SCDM model, the standard model of cosmology. So, to conclude our presentation today, the conclusion is the cosmic microwave background CMB is the oldest observable light in the universe and provides direct evidence for the Big Bang, confirming that the early universe was once hot, dense, and nearly uniform. Detailed measurements of the CMB allow cosmologists to determine fundamental properties of the universe, such as its age, composition, and overall properties and overall geometry. The CMB also plays a crucial role in understanding dark matter, dark energy, and the expansion of the universe at its tiny temperature. Fluctuations reveal how matter evolved into large-scale cosmic structures. Modern missions, particularly the Planck satellite, have made the CMB the most precise and reliable tool for testing cosmological models. For these reasons, the CMB remains central to modern cosmology and our understanding of the universe's origin and evolution. These are the references for our presentation. So that's all from us today. Thank you for your attention, and we hope to see you soon. Thank you. Assalamualaikum and goodbye.